So we've learned about electric force, electric field, and electric flux. And what we know is that a charged object has a field associated with it. And that field depends on the object, its charge, its shape, and so on. This is a simple point charge, and the field looks like this. And the field represents the strength and direction of the force that's going to be on a charge if you put it there, right? So the field exists even if there's no charge there, but to detect the field we need a charge. So we put a charge here and we detect a force and we assign a value to the strength of the field as the force per unit charge. And that number in newtons per coulomb is independent of the charge we put there, because if you put twice as big a charge, you'll get twice as big a force. You're going to get the same field, say 100 newtons per coulomb, no matter what charge there. But in the absence of a charge, the field is there, but there's no force. So similarly, if I put a charge here, the same charge, I messed it up, let me fix it. So the force field exists even if there's no charge. And there's an energy field that exists even if there's no charge. But to have energy, you have to put a charge there. So I put a charge there. Not only is there a force on that charge, but that charge has energy, right? Because if I let the charge go, it's going to accelerate off in this direction, gaining kinetic energy. So if it's gaining kinetic energy, there had to be an electric potential energy associated with that position. Now remember, last semester we used PE and we used U, and this semester we're pretty much just going to use the U. So we had PEG for gravitational potential energy, PE spring, or UG or U spring, and now we're going to call this UE, the electric potential energy. And how do we think about it? Well, let's remember what we know about energy. So here's what we learned last semester. And if you go to that equation sheet, you'll see this equation. The kinetic energy, we know energy is conserved. Work is the way we increase or decrease the energy of a system. So we write the equation this way on the equation sheet. And U are potential energies. Last semester it was gravitational potential energy, spring potential energy, and now we have electric potential energy. So in cases where there's no work done on the system, an isolated system, then the total energy of the system will be constant. And any gain in kinetic energy has to be a loss of potential energy. So the charge over here, it's like a ball rolling down a hill. It loses gravitational potential energy and gains kinetic energy. So it's going to be the same idea. Now, we did a lot of MOPS, and another useful way of thinking about it is if we rewrite this equation, this is K initial, K final minus K initial, and U final minus U initial, although in the MOPS we used PE. But if we rewrite this, we get, if you take the initial energy, kinetic energy, and the initial potential energy, and there's no work, it must be equal to the sum of the final kinetic energy and the final potential energy. But if there's work, the final energy could be bigger or smaller than the initial energy according to the work done. Oh, you need to remember what work is. Don't wait for me. Write down the equation of work. Think about work, right? You don't want to just be looking up equations on your equation sheet. What is work? Think back to last semester. So the most general definition of work is the integral of F dot dr. Well, you have to know what the dot product is, but we've seen that a lot in physics, and it's simply the sum of two vectors. These should be vector. There's your vector symbol. The F times the cosine of theta times the dr. It's the force times the little displacement vector times the cosine of the angle between them. Now, if the force is varying or the angle is changing, but in simple cases, it's just the force, the displacement, and the angle. So if we push a table with a certain force, a certain distance, that's a certain amount of work. If the table's sliding towards us and we push back to stop it, then you'll do a negative work, right? And you may remember when you move something, when the force is perpendicular to the motion, no work is done. Okay, that's a lot of stuff from first semester, but the basic idea of work is you apply a force over a distance, and you can either add or subtract energy to a system. So let's go back to our electric charge and think about all this relative to the force, the energy that an electric charge is going to have when it's in an electric field. Here's our charge in the field. But there's no force unless we put a charge. So if we put a charge here, we can talk about the force on it, and we can now, what we want to talk about this week is the energy on it. Now, we can use conservation of energy and the work equation to think about how much energy we have. What we want to know is how much electric potential energy does this charge have? So the first thing to notice is if I push it closer to the charge, will the electric potential energy increase or decrease? Increase, right? And if I move it further from the charge, it'll decrease. And if I move it really far away from the charge, there'll be essentially no electric potential energy. Right? It gets less and less, and once it's a certain distance away, it might as well be zero. So that leads to an important point that you're going to have to remember. The electric potential energy equals zero at infinity. So our reference is when the charges are far away, and as the charge gets closer and closer to the other charge, the energy is going to rise. Now, if we let this charge go, when it gets far away, the force will essentially become zero and it'll move away. It's going to accelerate it first, but the acceleration will be less and less and less. And so if we measure the kinetic energy when it's far away, that would be equal, it started at rest, the change in kinetic energy would be equal and opposite to the change in electric potential energy. So if we measured the 1/2 mv final squared, that would be the amount of energy we had. But a better way to look at it is to take this charge far away and do work on it. Push it into this position from far away. So let's see what that looks like. Okay, stay with me, try to follow this. So the charge, here's the charge Q2 that's far away, and I'm going to push it in. And so since as I push it, I have to push harder and harder, right? The force is getting stronger and stronger, is 1 over r squared. And just to keep the integral simple, let's do it on the x-axis, so it's a one-dimensional problem. So I'm going to start at infinity, and I'm going to end up at some x final, right? Some position where we're going to stop. So I'm going to integrate from infinity to x final. And the force is this, and the displacement is that, and since I'm pushing in this direction and the displacement is in this direction, the cosine of the angle between the f and the displacement is always 1 because it's 0 degrees. So the integral simply becomes this, and this, the result of this integral, when you integrate 1 over x squared dx, it ends up 1 over x. so I'm not going to do the calculus here, but what we end up with is this equation. When you do the integral, the x squared becomes 1 over x. And so our equation for the potential energy between any 2 point charges is simply this. It looks like Coulomb's law, only the r is not squared. That comes out of the integral, the work integral. So if we have a charge in a position here, its electric potential energy in that position is simply going to be K, Q1, Q2, over the distance between the two charges, not squared. So we have a very simple result, and we can now calculate the electric potential energy for any 2 point charges. And we can do it for more than 2 point charges and just add them up. But there's an anomaly that I'm going to tell you about in a minute. So if I release this charge and it has this much energy, all that energy is going to become kinetic energy when it moves far away. We can use conservation of energy to predict how much kinetic energy that charge is going to have when it gets far away. What's also clear is that if r gets smaller, which is what we thought, right? The energy gets bigger, and if r gets bigger, the energy gets smaller. But what if r is constant? So if r is the same distance from the charge, it doesn't matter where it is. So there's a circle here, right? There's a circle here where the energy of the charge is all going to be the same. I don't know if I can draw a very good circle, but... And so this circle maps out points where the energy is equal. So, and if there would be another, say the energy of that circle was 10 joules, and it's 1 over r, this would be 20 joules, and out here would be 5 joules, right? A circle twice as far away. And so we have these circles of equal energy. All right, a couple things. One is we know the energy at infinity. The electric energy is 0 at infinity. But if we have a negative charge, here's the anomaly. If we have a negative charge, then the energy becomes negative. And this is actually a physical thing. So if I move a negative charge this way, its negative energy increases. In other words, it's like going from a hole into a deeper hole. And since the energy, there's a greater negative energy, that means that in order to get it back to infinity, in order to take a negative charge from any position here and move it to infinity, it requires that we put in energy. So if you have the situation where it takes energy to get you back to 0 energy, then you've got to think of it as a negative energy. It's almost as if we define gravitational potential energy, mgh, as the distance above the floor, and then we cut a hole in the floor and we let it go down into the basement. If we call this 0, then the basement is negative, and the amount of energy it takes to get it out of the basement back to the first floor would be the energy, the amount of negative energy in the basement. So now we have this thing where we have opposite energies, positive and negative energy. So you're just going to have to get used to that. But for point charges, the equation works the same way. So notice, if you have 2 positive charges, the energy is positive. If you have 2 negative charges, the energy is positive. When you have a positive and a negative charge, the energy is going to be negative. So let's say we put a 1 Coulomb charge here, and we use the equation to calculate, and we get 10 joules of energy. That means if I put a 2 Coulomb charge there, we would have 20 joules of energy. So what we want to do is define a new function, a new concept called the electric potential. It's like the energy field. Just like we defined electric field as the force per unit charge, the energy field, the V, electric potential, is going to be the electric potential energy per unit charge. So if I take the 10 joules and divide it by the 1 coulomb charge, I get 10 joules per coulomb. If I take the 20 joules of the bigger charge and divide it by 2 coulombs, I get 10 joules per coulomb. So if I take the charge away, then we can say that this point where the charge was is a point where you will have 10 joules per coulomb for whatever charge you put there. So a 1 coulomb charge will give you 10 joules. A 10 coulomb charge will give you 100 joules, right? What we're doing is we're rewriting this equation. The electric potential energy now just becomes the charge times the electric potential. And since we're dividing the K, Q1, Q2 over R by the Q2, we're dividing the potential by the charge, we get an equation for calculating the electric potential for a point charge is just KQ over R. It looks a lot like the field equation, only the R is not squared. And so now we can, let me pause. So now if I draw this equal energy circle, the place where any charge will have the same energy, we can describe this circle by its potential, 10 joules per coulomb. Doesn't look like a circle, but imagine it is. And joules per coulomb, because it's such a common quantity, has a name. It's called a volt. So we're going to term that you're familiar with, volt, is just joules per coulomb. And so this circle, we can label it 10 volts. And the energy of any charge we put there is simply going to be the charge times the voltage. Just like the force on any charge in a field is the charge times the field. And then we could draw a series of other circles. If that's 10 joules per coulomb, this would be 20 joules per coulomb, and out here would be 30 joules per coulomb. And so we could draw a series of circles that would be equipotential lines, and that's what we think of as the energy field for this charge arrangement. Now it's important to remember that the reason a charge put here has the same energy is because it's the same distance from the second charge. Another way of thinking of it is, if you have a charge at this point and you move it this way, its energy increases. If you move it this way, its energy decreases. But if you move perpendicular to the force, its energy isn't going to change. So that goes back to our work equation, right? When you move perpendicular. So when you have gravitational potential, and anything that stays at the same height has the same gravitational potential energy. And so these equipotential lines will always be perpendicular to the field lines, because in order for the energy or the energy potential not to change, you have to move in a direction that's perpendicular to the force. Because if you move with the force, against the force, the energy increases. If you move with the force, you lose potential energy. So here's a summary of what we covered. The electric potential energy found between any 2-point charges is calculated by this equation. It can be a positive or a negative quantity, and it's in energy, and it's measured in joules. We have a potential, an electric potential function, which is like our electric field. It's an energy field, And any point in space has an electric potential of whatever the potential energy is divided by the unit charge. That's measured in joules per coulomb, which is given the name of volt, or capital V. And so if we know that what the potential is, we can calculate the energy simply multiplying the potential times the charge. And since volts or voltage is a common quantity, let's look at some practical examples of this. So here's a very simple practical example. We have two metal plates and we're going to charge them. So there's a uniform electric field between them. And how would we charge them? We'd use a battery. So supposing we take a 6-volt battery and we connect the positive terminal to this plate and the negative terminal to that plate, the battery will make this positively charged and this negatively charged. And the energy difference between the plates is going to be determined by the battery. And so the 6 volts of the battery means that there are 6 joules for every coulomb of charge that the battery moves. And so the voltage, the energy difference between these plates is going to be 6 volts. And if I take say a little positive test charge and I place it on the positive plate and I let it go, it's going to move from the positive plate to the negative plate like a ball rolling down a hill. It's going to gain kinetic energy equal to the change in potential energy. And the change, in this case, the change in potential energy is simply going to be this equation. So whatever the charge is, so if it were, just to keep things simple, a 1 coulomb charge, then it would gain 6 coulombs of kinetic energy and lose 6 coulombs. Now if it went halfway, it would lose 3. And so if we move the charge, if the charge moves this way, it loses potential. If the charge moves this way, it gains potential. But if it moves this way, it's going to have the same potential. So we could draw a series of lines. This is something we'll do in lab. If we drew 5 lines, 1, I don't want to draw them all the way, 2, 3, 4, 5, then this would be 1 volt, 2 volts, 3 volts, 4 volts, 5 volts, 6 volts, all the way across. And so the line in the middle, I didn't draw these very well, would be the 3-volt line. And so if it went from 6 volts to 3 volts, the change would be 3 volts, and that's how much energy you would get. So the lab and the assignment will have a series of problems like this and others where you will use these equations to answer questions and solve problems.